to the game planner.
Hello, everyone. So due to unforeseen circumstances, my CASSIDY from UNSW in Sydney couldn't attend this week, so I'm going to speak in her place. And I'm Gavin Brennan from Macquarie University in Sydney, and I'm going to tell you about what we've been doing in the Sydney area with regards to training the quantum workforce. So, you've probably seen a few talks now that have talked about the kinds of investments going on internationally. And so I'm going to show you another map here. Things have been ramping up very quickly over the past decade. Just in particular to highlight what's happening in Australia and Korea. So Australia, over the past, say, 25 years, we've put in roughly $1.5 billion US, and Korea is around 2.3 billion, so not too far apart. A big part of the investment is not just in equipment capital, starting up companies, it's in human capital. So as part of the National Quantum Strategy that was launched in Australia, there were 5 critical themes targeted: thriving research and development, access to secured infrastructure, trusted and inclusive ecosystem, standards framework, and key here is a skilled and growing quantum workforce. If you don't have that workforce, whatever great ideas, whatever great companies spin off or start up are not going to stay. Now, it's estimated that the global number of quantum jobs is going to get up to roughly 580,000 by the year 2040. But actually, not all those jobs are going to require the most strict and highest level training. A lot of them are going to require PhD training, but a lot of them are also going to require, master's and bachelor's training. So you have to have a holistic approach if you're going to actually prepare people for the jobs that are going to become available in this sector. In terms of sort of the dicing up of where these jobs are going to go, according to projections from CSIRO, which is a national lab in Australia, by 2045 we expect roughly 19,400 jobs. The bulk of them would be in the computing sector, followed by communications and then sensing and measurement. But actually, there's good reason to think that this figure is too conservative. There's been a sort of a reanalysis by Professors Langford and Devitt at UTS, who based upon some projections from the group Eureka, which I have to recommend is a great resource if you want to get updates on the worldwide quantum ecosystem. Project that we could see, in fact, really about 115,000 jobs by the year 2040 as part of the quantum workforce. In sort of building up a national strategy for Australia, part of that is going to try to play into the strengths of different regions and make sure that regions can interact well with each other. So we're a big country, and a lot of the population is focused around the coasts. And I'm from New South Wales. That's where Sydney is, sitting inside the state of New South Wales. And so they did sort of a skills assessment to look at what kind of capabilities are available in the different regions. And based on this, you get a sense of what might be priority investments and what might be good areas to focus training on. So I'm going to tell you a little bit about what we did in Sydney for training, what we continue to do. To give you an overlay of the kind of expertise, there are more than 100 quantum experts and growing inside Sydney. And by quantum experts, I really mean quantum 2.0. So this is, making essential use of, control of individual particles that are quantum, either atoms, quantum materials, or quantum degrees of freedom, photons, to enable entirely new technologies. And so you see the kind of breakdown here in computing, sensing, and communications. There's a lot of expertise, and much of the expertise has overlap in the three large areas. We recognized that in order to fulfill the needs of the National Quantum Strategy, we needed to actually make our own initiative. And so in Sydney, we brought together the four universities: Macquarie University, University of New South Wales, University of Sydney, and UTS. And we established what is known as the Sydney Quantum Academy. And the vision is to simply make a quantum-ready nation of Australia. And this involved an investment from the universities as well as the New South Wales state government, and to promote cross-sector collaboration, to develop being future specialists, entrepreneurs, and leaders in quantum technologies. And the key objectives are to train quantum workforce, connect the quantum community, promote and allocate for quantum, and advocate for quantum. And part of that advocacy does involve talking to decision makers, such as politicians, and also to provide trusted advice on quantum strategy to those decision makers. What kind of outcomes have we had? Well, since 2019, we've had 283 scholars. These are, they're just scholars that come directly through the academy. That number is growing. Over 23 million in scholarships awarded, and there are 29 countries represented, 31 industry partnerships, and the breakdown in these numbers of the scholars is 165 undergrad, 35 honors or masters, and 175 PhD, as well as we've also funded a small number of postdoc fellows. So you see that actually there's a good representation both at the undergrad and graduate level. And I've had the fortune of being able to train many of the PhD SQA scholars myself, which has been a fantastic experience. So what does the PhD program look like inside the Academy? Well, so as I said, there are over 170 scholarships awarded. These are importantly competitive 4-year programs. So when we founded the SQA, it was very important that we emphasize the need to go beyond what is the standard 3 or 3.5 year PhD program in Australia to 4 years. And that was a recognition that there's a lot of specialized training you need, including coursework that's not covered in most undergraduate programs. And so that needed to be supplemented by these extra months of training in order that we would be competitive in the world market. And fortunately, it's not easy to get the heads of universities to agree on these kinds of things, but we did, and they agreed to support these 4-year programs. Also essential in this was career development funding. So as part of the scholarship, the students receive some cash, which enables them to go to conferences and also to visit collaborators, many of whom are international. Of course, part of the SQA training included access to coursework that's specific in Quantum 2.0, and also as well as access to seminars, workshops, and networking events. leadership and transferable skills. And recruitment. As part of the undergraduate program, there was a 6-week quantum research studentships in any of the partner universities, honors and master's scholarships, and industry experience programs. And then as part of outreach, we had 2 to 3 day quantum camps for high school students, which were very successful. Many of these received very glowing reviews from the participants. These included hackathons and just exposing the students to quantum, even though we might think it's too advanced for high school students, not at all. It's jumping into the deep end is sometimes the best way to attract some of the real talent. Partnering industry sponsors, and a large part of this was diversity focused. So, trying to get communities who aren't usually joining into the quantum space, including students who may be the first member of their family to go to higher degree research, and as well as open days and career fairs. So I did want to mention that a part of the Sydney Quantum Academy was to engage with industry, and that means allowing students the space to have internships and to put a pause on their PhD program so they can work directly with the company to get experience, be very useful when they finish. So I have a student who just did a pause on his PhD for 6 months to work at a quantum error correction software spin out from the University of Sydney known as Iceberg Quantum. So he just finished a few days ago and found the experience very rewarding. So if you're looking to maybe kind of mimic this kind of program, I think it's really important to give the students in the program space to explore these kinds of things. It might mean that it takes a little bit longer for them to finish their PhD, but in the end, it really is worth it. As part of linking and training with industry needs, beyond the Sydney Quantum Academy, Australia has been gracious in funding what are known as industrial training transformation centers. So these are 5-year funded centers that are focused on a particular research area where the students are encouraged to work very closely in industry in that research area. So 2 of these are FLIC, Future Leaders in Quantum Computing, and QTech, Current and Emerging Quantum Technologies. So I want to just talk a little bit about FLIC. So Stephen Bartlett, who gave the talk this morning about Quantum Australia, is the director out of the University of Sydney of this Industrial Transformation Training Center. And the mission here is to train skilled and diverse, industry-connected research workforce that will lead Australia's quantum computing future. So that is the mission. And you notice it is actually more targeted than the Sydney Quantum Academy, which was really all of Quantum 2.0. This is focused on quantum computing, largely in recognition that the Sydney area, the US, or New South Wales in particular, has really built an expertise at the full stack of quantum computing, from materials design to engineering gates, to designing error correction protocols, as well as the algorithms that will run on quantum computers. So there are 3 main strategic priorities for this center. One is research, of course, pushing the boundaries of our knowledge, training and development to cultivate highly skilled, adaptable workforce, and industrial transformation, which is, of course, the mission of the center. That's to build strong bridges between academia and industry, transforming research breakthroughs into real-world solutions. And it sounds like a lot for 5 years, but already some of that has been handed out, and the center has only been up for a year. training program within FLIC involves sort of three pieces. There's the technical capabilities, addressing key research challenges across the quantum stack, devices, architecture, and algorithms, as well as leadership through agency. So empowering candidates with the skills, networks, and career agency to lead in the emerging quantum industry. Some of this means you've got to put some faith and trust in. So you don't leave like all the decisions to the senior professors. You give some of the decision making to earlier career researchers, and you know, that kind of leadership potential then filters down even to the trainees. And finally, transforming the quantum ecosystem. This is very important, creating an inclusive, forward-thinking quantum workforce by increasing participation of underrepresented groups. This is an ongoing challenge, and we've seen some successes already through the SQA, and we're seeing that continue through FLIC. Who are the people involved? Well, here's the cast of the chief investigators. And something I want you to notice here, first of all, I mentioned that this is a New South Wales base, but actually included as one of the nodes of FLIC is the University of Western Australia, based in Perth, that's far on the west side of the country. And the University of Western Australia has some strong expertise in quantum algorithms development through the leadership of Jingbo Wang. So, it's really Sydney plus UWA. And one thing I want you to notice here is that this is not just a bunch of professors. These are early and mid-career researchers whose career trajectory is going up, and we want to cultivate that for further success in the field. Partner organizations are very key for this. So FLIC has secured partnerships from some of the leading quantum hardware and software companies in the world, including Q-Control, PsiQuantum, Inflection, River Lane, and so forth. And this is very important because these partnerships lead directly to internships and jobs for the graduates. And the FLIC offers PhD scholarships with 4 years plus industry engagement, and the students undertake research aligned to quantum devices, architecture, and algorithms. So the vision here of FLIC and SQA partnerships is a Quantum Ready Australia. So I think you can see that through these programs, the experience program with a PhD, which includes not just taking coursework and doing their research, but also participating in seminars and leadership training programs. Going down not just from PhD, but to the undergraduate outreach programs. That's a combination of these efforts provides a complete package, so that if you're a curious high school student, you know that there's a program there where you can learn from some of the best and have a chance for a real job in quantum. So let me just finish up there, and I'll leave it here with, well, sorry, I've nearly run out of time here, but this is some slides about this particular program at UNSW, which is a training program in quantum engineering. They had one of the first undergraduate, in fact, the world's first undergraduate degree in quantum engineering. So, thank you.
Question and answer.
Yes. Yeah, so it's both. Yeah, absolutely. So, we're going to be finding a case where when we actually have devices that reach utility scale, which I do think is going to happen in the early 2030s, that we're going to need people that can translate problems that companies have now into to problems that can be run on quantum computers. If they need to like map a differential equation to a quantum circuit, well, you're going to have people that know both ends of that. And they're going to have to talk very closely with each other. They're going to be partners, in some project. So yeah, you would want to include those people.
Okay.
So we don't have a specific exchange program, but I will say that a lot of the scholars are international. So in fact, nearly all of the SQA PhD scholars I supervise have been international. But the programs will fund both. Yes, absolutely.
Thank you for the presentation. Next speaker is Nguyen Nam and KAIST.
So good afternoon, everyone. First of all, thanks very much for this wonderful opportunity to share our graduate program, KAIST. And my name is Nguyen Nam, and I'm the chair of Korean Graduate School at KAIST. And here I will introduce you to KAIST research and education, and also innovation and academic exchange. Also our global collaborations. So how we are educating the next generation collaborators. So as you can see here, the specialty of this program is actually we are operating this program together with KRISS and METRI, the top two quantum research institute in Korea. So in addition to the excellence in the quantum research, actually we are located very closely within 3 kilometers of circumference, as you can see here. And I think this helps us to have a stronger collaboration. Okay. So let me introduce you, just for the people who don't know the KAIST. KAIST was established in 1971. It's a little more than 50 years old. So compared to the other university, it has a very short history. And the purpose of this establishment, main purpose is actually industrialization of Korea. After Korean War, there was nothing. So there is a strong strategic plan to have industrialization of Korean communities. So the main purpose is actually educate the national core manpower and develop industry of Korea. So I think it was very successful. So as you can see here, from some number, it's like here from these some numbers. Now we have about 11,000 undergraduate and graduate students. It's like 4,000 undergraduate and 7,000 graduate students because we are a research-oriented university. Quite large number of students are graduate, okay, and total about 700 faculty members. One thing pretty impressive, I think, is we were selected as the most innovative university in Asia for several years. And also, as I mentioned, the fourth main purpose of KAIST is industrialization of Korea. So it's 25% of R&D workforce in Samsung Electronics is actually KAIST graduate, and 20% is all beautiful university professorship is KAIST graduate. You can find some kind of key players in the industry, like Samsung or Hynix and LG. We have a lot of KAIST alumni. Okay, KAIST has become a hub of innovation, also in quantum science and technology. So there is no subject ranking for the quantum science and technology. So I brought up some subjects that are very closely related to the quantum science and technology. So, for example, physics and electrical engineering and mechanical engineering and computer science. Those subjects, actually, we do have participating faculty members in our graduate programs. So as you can see, they are very good, recognized worldwide as one of the best programs in the world. Nature Index of the Physical Science, you guys all know that the top 10 are all Chinese university, but I mean we are also recognized very well as well. And if you think about the enabling technology for the quantum, we do have a very good research in the semiconductor and AI program as well. Okay. So the main goal of our quantum graduate school is nurture the next generation quantum world leaders. This is, as I told you, collaboration through the KRISS and NGV. And they do have a lot of opportunities in the research and other things, but I mean, most of all, I like to emphasize the fact that they are all supported by the scholarship, so they can concentrate their own research without worrying about other things. And we also emphasize the collaboration synergy. So, I mean, students can benefit from joint advising program, for example. So they can obtain the expertise from various different domains. So the students have could select an advisor from 2 different research institute in this program. And also we have a joint education program. So all the lectures can be delivered to the students from different domains, again, with a different expertise. We also have a research opportunity in the industry, like big companies or startup companies for the quantum, and also research institute as well. So we do pursue the innovation in the quantum research, and because we do have a lot of participants, very close to the 50 faculty members participating in this program. So we do have a broad range of quantum researches. So let me show you they are all independent researchers, but for the conveniences, I categorize it into the several programs. Let me start from AMO. We do have a world leading researchers in AMO groups, studying like a Bitburg atom quantum computing, and also study the quantum many problems like normalization or phase transition using a large number of atoms trapped in optical lattice, and also the interface of atomic qubit and optical imaging, so they can apply to utilize that into the digital neutralized quantum computing. So Professor Chilgan is sitting over there. We also have a quantum materials group. Typically, they are interested in not like quantum 2.0, but usually quantum 1.0. So they are interested in the physical properties of these quantum materials, novel or new kind of phenomenon or properties. However, they try to utilize this quantum material in more realistic applications. For example, they would like to have like a spin cubic quantum future. I don't know it's going to be possible in your future, but I mean, it's definitely interesting, like a project. Also, they can have some kind of crystal effect. And this two-level system also can be used in this sort of application, either in the quantum sensing or quantum computing. We have a quantum device group in the condensed matter experimental group. Okay, so they are interested in developing like a gate-tunable superconducting resonator can be used in the like tunable copper loads. Also, like energy-efficient quantum neuromorphic computing. And also the part of this team is actually the National Superconducting Quantum Computing Center. The researchers from this center embarked in this program as well. Oh, I didn't tell you that since we have 3 research institutes participating in this program, the blue is KAIST participant, orange is KRISS participant, and green is actually probably actually is here. Yes, actually participant like that. Okay, we also have a group of theorists working on this quantum science program as well. So they study the hybridization of like classical and quantum computing, developing new algorithm for the quantum computing, or find a near-term quantum advantage with these NISQ quantum computing systems, or they are even interested in solving some kind of fundamental like quantum information processing problem as well. We do have a large number of participants in quantum optics and nanophotonics. Sometimes they call that as a quantum photonics. So large number of people participating in this. They are making photonic integrated circuit, also single photon generation and detection, and also a lot of like devices can be utilized in photonic quantum computing system. Okay, we do have all those researches are quite like well recognized by the major journals and so on. But I will just flash them to. It's not very important. Because of these potentials and research capability in our university, our program is well recognized by the government as well. So national or local government, and we got tremendous support from the government. So let me introduce some of these initiatives to you guys. So let me start from the Quantum X Research Building. This is now it's a project is going on. We secured the budget about $20 million for this project. This budget is only for the constructions. We do have a separate budget allocated to enhance the research in between these domains. So here quantum is a quantum, and X is some other disciplines can be enabled by this quantum science and technology or enhanced. So it could be mathematics or chemistry, life science, or material science, and so on. Here, people are surprised that this small amount of money that you can build this kind of nice building. Yes, this is possible because we are in South Korea. We do have a very efficient like construction companies. So this is about, I calculated it's about 25 to 30,000 square meters. It's not a small building. So, and very nice program. And KAIST also play central roles in Korea's quantum national infrastructures. So this is a National Quantum Fabrication Center hosted by KAIST. It's about $32 million project. It includes not just only building. In this case, the building is pretty small, but I mean this is part of the money goes to the equipment and the fabrication instruments. So this is open quantum fabrication facilities. So like graduate students or researchers from the startup or spin-off company, they can go into the fabrication facility directly and do whatever they need to do. For example, developing the prototype devices or test their own recipes, new recipes in this verification process. So I think this initiative will promote open access, whatever, and contribute to the development of new kind of industries starting from the university. This is again starting from the collaboration between KRISS and NNFC. NNFC stands for the National Nano Fabrication Center, which is also located in KAIST campus. Okay, so we developed this quantum graduate program at KAIST, and this is another like a government-funded project. So it's a quantum school giving the PhD degrees, but what I'm talking about is we share our quantum education platform together with 8 other national universities in Korea. Very similar program like a CASSIDY Quantum Academy, I think. Because we share the education curriculum, also research infrastructures, also opportunity for the industrial experiences and so on. Okay, so again, this is I think very useful. 8 national universities, they do have a very prestigious program as well. However, I mean by themselves it is difficult to like operate their own like quantum curriculum. So we all work together to have this quantum education consortium. So another thing that I like to share is international collaboration. We have a lot of international network. But one thing that I like to emphasize is this global partnership together with MIT. This is promoting the alliance for kind of frontier researches in various domains. Like a lot of people working like to work together with the MIT theoreticians, and also they do have a very strong expertise in the experiment as well. And we could have a possibly like an exchange program together with MIT. So this global partnership support not just only joint quantum research, but exchange program and the fellowship together. We hope with this program we nurture the next generation quantum leaders in this program have a global perspective of that. And this is also $16 billion project. Part of the program is actually our program is a graduate school, so we try to allure the undergraduate student to be interested in this quantum. So we have like an inspiring undergraduate workshop, like a quantum winter school, and MIT professors regularly fly to here to have interaction with these undergraduate students in South Korea. The undergraduate students are very talented because we selected just only, typically we select only 40 undergraduate students. So they do have a special opportunity to interact together with faculty members from KAIST and MIT. And this is my final slide. So KAIST Quantum Program, KAIST Quantum Graduate School stands at the intersection between the education, and research, and innovation. We are building the future of quantum future of Korea together. And I learned a lot of interesting and excellent research and talent development program here, and found that the number of our collaboration network is not very active. So with this forum or this event, I hope we can have more like interaction between this Asian university or institute. Thanks for your attention.
I was just curious, with the quantum X, have you found interest from other disciplines like chemistry engaging with quantum in this program?
Chemistry, yes, definitely. But you know, as you know, the requirement for the resources for the use case or real application of chemistry is kind of not in near future. However, they are interested in a part of their. So, what I'm saying is, so are there any real application in these days? Maybe near future we do have that kind of quantum chemistry application, but our researchers in KAIST campus, for example, they collaborate together with one of the startup companies to make the efficient quantum algorithm working at this layer. So that's called that's combining the variation of quantum eigensolver together with the quantum system. So it's called high VQE. And they are interested in some part, but I mean not really active, I think.
Any other question? Okay, thank you. The third speaker also has been changed. So the next speaker, Kim. Kim. I'm currently a postdoc in KRISS, and today I'm a substitute presenter, so I only had 1 day to prepare, and I'm afraid that my talk is not really related to this theme, but maybe before that. So today I'm going to introduce some works currently doing in the neutral atom quantum computers in KAIST and KRISS, one of the two institutes working in the neutral atom quantum computers in Korea. And as you might know, the tweeter-based neutral atom quantum computers are very highly being interested by, for example, the high scalability of, for example, 6,000 physical qubits, and also multiple connection and zone-based quantum computing, which able, for example, 48 logical qubits currently made in Harvard, and some other very fascinating, interesting properties of this computer. So that's why it's been many research a lot. And to begin, I want to briefly introduce what the neutral quantum computer is. So neutral atoms are qubits, used as qubits by, for example, choosing two states in the atoms as an excited state and a ground state, and coupling them with lasers. And if we, for example, choose two states as a 0 and 1, this constitutes a computational bit, and this becomes a quantum bit, and it's a qubit. And the single qubit is operated by lasers by atom light interactions. And for example, this is an operating video videos from the KRISS 171 interpreting machines. And because we want to make a quantum computer to work, we needed 2 qubit operations. So to make the 2 qubit operations, we have to interact 2 qubits, and because atoms are neutral, they do not interact with equal forces, for example. So we have to, for example, excite this atoms into a highly excited states, which is we call the Rydberg states. And this highly excited Rydberg atoms have a very large dipole moments, therefore they interact with the dipole interactions. And if, for example, 2 atoms have the same Rydberg states, they interact with the some kind of a dipole interaction called the van der Waals interactions, which has a form of C6 over R2D6. So it depends on the interatomic distance of the atoms. And often we use the neutral atoms trapped by the optical tweezers. And these optical tweezers are some kind of a focus array of lasers. And because it's a focus array of lasers, the atoms are attracted to the focus of the lasers by the dipole forces. And by generating an arbitrary array of lasers, we can configure the atom arrays arbitrarily. And one of the many ways to generate such a focus array of atoms is to make hologram-based optical tweezers by, for example, these spatial lane modulators, which generates a hologram. And by changing this hologram, we can configure any atomic arrays from it. And also, additional to this, we have a free-moving optical tweezers by the acoustic gradients, for example, in AOD or AUM. And we use to move the atoms with this kind of acoustic gradient and move the qubits in real time. And okay, so that's the overall properties of the neutral quantum computers. And actually, there are about 4 places which is currently having or being building a tweezer-based neutral quantum computers in Korea. And for example, in yellow circle is where we are here. And in Daejeon, there's a KAIST and KRISS having a 171 ytterbium atoms and 87 rubidium atoms tweezer machines. And also in Seoul and Korea University and Hwang and Postec, they are also building tweezer atom machines. And I have been working in KAIST lab as a PhD student until this February, and I'm doing my postdoc in KRISS from this March, so I'm going to introduce 2 machines and the words from these 2 machines. And firstly, I want to introduce the 87 rubidium machines in KAIST, which the team is led by the Professor Jae Gan. There's also a team from Professor Dong Kim, but I'm from this lab, so I'm going to introduce this lab. And for example, this is an operating video of this machine. And this is the one of the first tweezer machines in Korea. And so currently only tweezer machines that are operating with the Rydberg states in Korea. And this is the first machine in the world to demonstrate the 3D atom configurations and SLM-based rearrangement. And it can trap up to 200 tweezers. And it can deterministically configure the atoms up to 20 or 30 atoms. And from this machine, we have done several works. First, I want to introduce about the optimization problem solving with this machine. So, as I explained, the 2 Rydberg atoms interact with the van der Waals interactions. And if the atoms are very close together, they will have a very large van der Waals interactions. Therefore, when they are very close, they will have a double Rydberg state. Our state is being blocked from the transitions because they get a lot of energies. And this kind of phenomena is called the Rydberg blockade. And so when atoms are far away, both atoms can excite to Rydberg atoms. However, they're very close, only one of the atoms can excite to the Rydberg state. And using such properties, we can, for example, map optimization problems into atoms. So for example, there's an optimization problem called the maximum independent set problem, which is the NP-hard, has an NP-hard time complexity vertices, and if we map this mathematical graph into atoms and show in the middle, and then we do operations using such an Rydberg blockade, the red atoms, which excited to the Rydberg state, will become a solution of this problem, because the maximum independent set problem has a cost function, same with the Hamiltonian of the Rydberg atoms. And using so, we have solved or did experiments to solve the MIS for quadratic graphs. And for example, this problem can be mapped into a real world problem. For example, if I want to make, for example, an ice cream kiosk in this map, and the constraint is that I do not want to place the kiosks neighboring each other to avoid the competition. And for example, we can map the map of this city into an atom array and do a quantum computations to solve the problems. And here where the atoms are gone, present the Rydberg states, which is a solution of the problem. And this is a solution to place the kiosk in the real world problem. So for example, and this kind of approach was done for some quantum computation companies such as Cura and Pascal. And, yes. And also, actually, direct embedding of this MIS problem is easy, because naive embedding of MIS problem could be approximated very easy. However, when we map this MIS problem to a general MIS problem, which requires the all-to-all connectivity of the atoms, the problem becomes very hard. It's nearly can't be approximated. So to do so, we introduce the atomic quantum wires. So we have a chain of atoms to connect all atoms. For example, we connect 2 and 5 atom, number 2 and number 5 atom with a chain of atoms. Then we can the chain of atom work as a Rydberg blockade at a distance. Therefore, we can achieve all-to-all connectivity in the atomic quantum wires. And general MIS problem could be achieved from this kind of embeddings. And you see also all kinds of optimization problem based on Rydberg quantum wires. These papers were published from our UK. Also, another application of the Rydberg interaction is that we have been seeing that using application of Rydberg blockade. So there were 2 cases where atoms are not blockaded and being blockaded. And actually, there are the intermediate regime where it's nearly blockaded and not really blockaded. And they're using in the intermediate regime, we can directly use Rydberg interactions as a phase gate. And for example, because the Rydberg interactions has, for example, a ZZ term, therefore it works as a phase gate. And there was an experiment realizing the C phase gate using a Bender-Russell interaction directly in our lab. And for example, as you can see from this, the Van der Waals interactions can generate entanglement between 2 atoms. And this kind of applications are used for many experiments. And I want to introduce the 2 applications of this Rydberg interaction-based entanglement. And one is the quantum state tomography with the position of ANSA. So there's a system of interest, data qubits, and it evolves with the Hamiltonian interest. And we have an unknown state, for example, row after the evolution. Now we want to figure out what this state would be. And to do so, we have to take a shot from the various visual bases to figure out the whole shape of this quantum state row. In the quantum sense is to figure out the unknown state row by the measurement of the row in the distinct basis. And to do so, we introduce the ANSA atoms around the data qubits. And by the position of ANSA, we generate the measurement basis. And from this different measurement basis, we could generally figure out every information from the row. And this is possible because Rydberg interaction depends on the interatomic distance. Therefore, the interactions are tunable with the atomic positions. And this position-dependent Rydberg interaction allows the ANSA position as a new measurement basis, because ANSA and data qubits would entangle in the different aspects by changing the positions. So the full construction of the data qubits could be possible by introducing the many number of measurement answer positions. And yes, this is a whole process. Yes, so we, for example, have a data qubits and an answer qubit, and we prepare the data qubits into unknown state, for example, a Bell state, and we entangle the atoms, answer atom and the data qubit together, and we get a probability distribution from the joint distribution, joint density matrices. And from measuring this probability distribution from all very many answer positions, we get sufficient information to reconstruct the unknown state. For example, in this case, the Bell state, and we can reconstruct the unknown state row by, for example, a maximum likelihood method. And this kind of method actually worked well for 3, 4, and 6 atoms also. This was one of the applications of this Ripper-based computer entanglement. Another application of this Ripper-based entanglement is to simulate, to a quantum simulation of some new model. So, for example, we want to simulate the spin exchange dynamics, because like spin exchange dynamics is very well many shown from the real world, magnets to photosynthesis and all. And to simulate, we need to have a quantized model. So, for example, we have a spin model with all x and y and z spin interactions, and if the x and y interactions are same, this x, y, y interaction turns into a spin exchange dynamics, which now we can simulate such dynamics from the Hamiltonian model. And to generate this kind of Hamiltonian model, we need to address atoms with a very large tuning delta, and in this case, this, for example, up-down states go to downward states, say with 2 paths, and they generate spin exchange dynamics. And this spin exchange interactions come from the 2 paths, the path 1 and path 2. And if there were no Ripper interactions there, the 2 paths would be destructively interfered. Therefore, we cannot have any spin exchange dynamics. However, thanks to the Ripper interaction, we can have such a spin exchange dynamics. And this is an example of the spin exchange dynamics simulated. And we can see that it very well matches the theory. Also, we can see somewhat on the 7 out of chains also. And also, now if we have 2 excitations, the ZZ interaction term become very important, and the ZZ interaction term uses the bonding of 2 excitations now. And because of the very large interactions, ZZ interactions, we now see a bounded motion of the 2 upspin bound states. For example, if we have a bounding energy U very large at 7 MHz, and if we have a spin exchange dynamics J, interaction J, which would split the 2 upspins in the bound state. And because the splitting energy is very smaller than the bound energy, no such splitting can happen. However, such a bound state, the motion that preserves the bound state can only be happening. The correlated motion from this kind of bound state can be only allowed dynamics, and we can see such a correlated motion from the existence of the bound state. And also, because the van der Waals interactions are the long-range interactions, we also have a loosely bound state, which has next nearest neighbor interactions. And this kind of bound state also could be observed from this kind of Hamiltonian case. So it's sort of using a Ripper quantum computation of the optimization problem could be solved, and also using a variable quantum interaction by changing the interatomic distances, quantum state tomography, and some kind of simulation using an quantum simulation of some model could have been done as an example. And I'll briefly introduce the turbine fusion machine in KRISS. And actually, the turbine fusion machine first divalent 2D machine in Korea, and it has a high fidelity, high survival rate imaging currently. And yes, we do not currently have a rigorous excitation yet. And one very interesting thing about the 171 ytterbium atom is the fermion ytterbium atom has a natural nuclear spin, and this nuclear spin is very stable among external, for example, noises, and this is a very good qubit system. And also, ytterbium atom has a metastable qubits as a main qubit, and metastable states, ground state qubits, and this kind of so we have a natural two qubits in the one atoms, and yes, this kind of atom is very good for quantum information. And there are two additional transitions in the ytterbium saying we have achieved the high fidelity, high survival rate, and 9% of fidelity and 99.6% of survival rate for the 556 nanometer imaging currency. And now I'm working with the 399 nanometer imaging because the ultra computer has a bottleneck for very slow waiting time, and one of the bottleneck is the slow imaging. For example, imaging costs, for example, 10 millisecond order time, where the gates are only a microsecond order. So shortening the imaging would be very helpful. And also for the quantum error corrections, we need multiple mid-circuit measurements, and therefore, for example, a very simple steam code requires a 6 imaging part, 1 logical qubits. Therefore, it's very time consuming. So therefore, it's very important to make a fast imaging. And also for erasure conversion or something, and the other aspects are very important to. Okay, so to briefly introduce, we have preliminarily did a 399 imaging quickly, and also number result imaging with the 399 imaging. And so in summary, it's in KRISS, I'm currently working on this best 399 nanometer imaging. And thank you for listening. And yes, KRISS, there are the graduate students from the KAIST Quantum Graduate School, which Professor Kim just introduced. Thank you.
Which was real physics topic of this session. Question? Yeah.
How can you resolve the issues of atoms blown away with
During the fast imaging. That's true. So actually, we need a very deep trap for currency, and we might need additional cooling beam together with this imaging. That's the final.
Okay. Thank you. Next speaker is Kritsana SRAKAEW. Yeah, next speaker is Nguyen Nam.
of Science and Engineering and Technology from the Ministry of Science and Technology of Vietnam. Vietnam in the process of developing a plan for quantum technology development. This presentation outlines Vietnam's strategic approach to quantum technology development, emphasizing the critical importance of seizing the current narrow window of opportunity to build a strong quantum innovation ecosystem. The presentation is trust around Vietnam's national commitment, exciting strengths and practical four-step action plan with a call for regional collaboration through APEC. Why quantum matter for Vietnam? Quantum technology represents a transformative force that Vietnam cannot ignore. The Prime Minister has identified quantum technology as a strategic priority with Resolution 57, setting a APECTP target to develop and master quantum and post-quantum cryptography by 2030 to ensure national information security at super secure level. This is not merely technological pursuit of master of nation security and future cooperative. The window of opportunity of narrow quantum revolution is unfolding now, and Vietnam must act decisively to build demonstrate capacity before the landscape becomes more competitive. What we bring to the table? Vietnam possesses several compelling advantages that position Israel quantum technology development. First, the nation has a solid foundation development in the mathematics and physics combined with a young that makes it ideal for absorbing and advancing new technology. Second, Vietnam has a significant deposit of high qualified scientists working at leading quantum research center worldwide. This policy Vietnamese aspect represents a valuable resource for cooperation, knowledge transfer, and potential repatriation. Thus, rather than competing only in general purpose advanced nanotechnology, Vietnam can focus on specializing high-level quantum chip such as quantum number generation. The four-step action plan. Step 1, build domestic R&D capacity. Vietnam must establish national quantum technology research center at leading universities such as Vietnam Academy of Science and Technology, Hanoi National University, Ho Chi Minh City National University, and Hanoi University of Science and Technology. This requires fostering strong cooperation between industry, academia, and government. The treehouse model, building domestic ID capacity, is processing of mastering core technology and achieving sales reducing dependence on foreign restricted technology. Step 2, develop human resource. A skilled workforce as is essential for quantum technology advance. Vietnam should implement dedicated scholarship programs such as training 150 PhD students over 5 years foundation quantum sector. The nation should also open postgraduate course is quantum technology of university. Step 3, double down in cyber security. Vietnam should adopt a two-strand cybersecurity in the near term. Post-quantum cryptography should be deployed worldwide across exciting system. PQC algorithms are mathematically proven for implementation and work with current infrastructure. For the future, Vietnam should invest the research, testing, and pilot development of KAIST. Step 4, forced international cooperation. Vietnam should actively participate in international forum and organization on quantum security. Developing quantum technology and ensuring cyber security in the quantum era are global challenges requiring collective action and trust cooperation. APEC present a new unique opportunity for regional collaboration through several mechanisms. Best practice sharing. APEC members facilitate the exchange of nation quantum stress, ID funding model, and open capital development initiatives to learn from each other experience. Joint identity. The region should propose cooperative research on quantum application, addressing regional challenges such as climate change, personalized medicine, and optimized logistics. Standardization for digital security. APEC members should work toward common standards for Vietnam quantum technology development stress its ground is planning ambition by building on exciting strengths, investing in global capital, adopting a clear security roadmap, and fostering international cooperation. Vietnam can position itself in international cooperation. Vietnam can position itself as a key player in the global quantum research. One contribution mean fully to business security and property through APEC cooperation. Thank you.
So, any question? Okay, then we'll go to the next speaker. That speaker is the early morning David.
All right, thank you very much. Thank you to Professor An for putting on this workshop and for the hospitality that you have shown to us. Appreciate that very much. I'm going to talk, it's the second talk from New Zealand, so I'm sorry, Professor Holzberg's name off my first slide. But I'm going to talk a little bit about facilities and collaboration in New Zealand. The first part is just about all of New Zealand, and the second part is about my institute in particular and how we work with the rest of the Asia Pacific region already. And I want to suggest there's an interesting model to look at. So here we have an interesting chart, and you can see this is the number of orbital rocket launches by country per million people, and you can see that there's the US, and Russia, and China, and so on. And you can see New Zealand is way off the scale. And that's because we always do everything per capita, because we're a small country. And so you might be surprised by that. I think in terms of absolute terms, we're about number 3. And this came about because of some innovation in New Zealand around reusable rocket components, engine developments, and so on. But really, the major technology came from the US. And it's a very good place to launch rockets. And the point I really want to make here is that even though we're kind of small and we are isolated, we're physically isolated, we're quite comfortable with doing sort of niche technological innovation. And I think, as you will understand, obviously we can't keep up with the big guys, but we can make some contribution. And a second illustration of this is we have strengths, I think, in material science. And in fact, I could have mentioned also strengths in quantum optics. So Professor this morning who got the award, Zola, did some of his early work in New Zealand with dam walls, and Professor Holzberg is director of the Dell Walls group. So there's a connection there. But this one here is superconductivity. A group at my institute at the time discovered probably the second useful high-temperature superconductor, and it was patented back in 1988. But I want to show you this picture here because the scientist in charge who was doing this work actually went to Parliament, government, and showed them a working experiment using high-temperature superconducting, because he wanted to convince them that they should put more investment into the area, and he was successful. So I think this is an important lesson for all of us, right? You've got to convince your political masters to invest, and this is something we're struggling with a bit in New Zealand, but more clearly from the example of Australia, they have been able to convince the government to invest well in that area, a little behind it. But that investment in superconductivity back in 1988 or so on has led to some remarkable things. So maybe last month, a low temperature plasma thruster went out into space and using low temperature superconducting coils. So it has facilities, I don't think I need to dwell on this too much. But in New Zealand, we do have some modest capabilities. We have some facilities for fabrication, AV machine, we have where we make nitrides, so on, learning electronics, chips. So we have some facilities. I think, as most people say, you kind of would like more. I think we have a particular problem with getting very large investments, but in general, our researchers are able to get good work done. We have supercomputer platforms available to us. This is for national infrastructure. And we have most of the normal tools that you might expect for materials characterization and testing are available. And so, in fact, there's even a database of the kind of material technologies you might be interested to use. So anyway, I don't need to perhaps go through the details of that, but really just make the point that we have facilities to support niche quantum technologies already available in New Zealand. Right, so in terms of collaboration, according to Elsevier, 63% of New Zealand's published output involves international collaboration. And that's just really a consequence of being small, right? You've got to find colleagues who do something that's similar. You won't really find them in New Zealand, you've got to go offshore. And I think we do welcome collaboration, both people coming to us and us to your facilities, so we're very open to that. And this ratio is much higher than the average of 21%. But nevertheless, we do and need to collaborate. The QTA group, which we're both part of here, is actively collaborating with institutes in the US, UK, Germany, Singapore, Japan, kind of through government negotiation, government direction, government agreements. It's recently in New Zealand was a Korean call, as mentioned this morning, quantum communications. And individuals do collaborate quite a lot. Australia, China, France, Singapore, South Korea, and there's probably many others as well. So we're certainly open for business regarding collaboration in quantum technologies. Now, so that's just the sort of the New Zealand scene. Now I want to turn to more activity institute. In the sense that we are a national metrology institute, and we've already heard from the Thai MIT, and there's others here who are part of the KRISS part of that system. And the reason why I mention this is because obviously many countries here, Korea, Japan, Australia, have already got a lot of activity going in quantum technologies. But APEC is much bigger than that. It's over 30, 40 countries. And some are yet to even start. So I just want to share a few experiences where it might be helpful for those economies who are thinking about trying to get into quantum technologies. And so most countries do have an NMI, and of course we already heard this morning about the electrical standards. Metrology is built on quantum standards, so we're very used to running quantum systems, have been so for 30 or 40 years. And so it's people who do electrical metrology, very experienced projects and precision measurements. We all have Josephson Knowledge systems and common Hall systems. And these work extremely well by parts of 9 people. So I just want to talk a little bit about that. Already, many MIs have the expertise in sensitive quantum measurements. And it's interesting to look around the world, places like NPL, the UK, even NIJ, and even the initial expertise has probably come from metrology to get some activity going. Talk about trained workforce, and that's going to get we need leaders, not 2 years. But if you need people today, go to electrical metrology. You further temperature control. We want sort of 0.1 degree. That's not easy to achieve. In fact, if you employ an engineering firm to do your temperature control, they'll struggle with below about half a degree. Not very useful level of accuracy. There's a famous building in Finland where they went to the extreme. They managed to achieve something like 105 degrees accuracy with the temperature. So the way we did it was we actually had conventional design and we completely changed it because you don't want air coming down on top. You really want it coming from underneath. In fact, what we end up is air coming from the sides, fairly gentle air, picking up the heat and escaping. That kind of method you can get 0.1 degree. And kind of where I'm heading is if you're about to build a building from quantum standards or quantum technologies of any kind, then maybe think about this first, because if you have a good temperature control of the bag, it just makes life easier. Now, you might have project experiments, all the electronics running at a good temperature. So, make life easy for yourself by perhaps getting it improved until it works well. So these are just the key design conclusions. So I'm going to describe it. Bring the air gently and take it up out of the ceiling. And that way you can achieve pretty good results. Second is the environment. Maybe not so important, but certainly for low noise, low electrical noise, you do need to take care. We're aware of many cases where people running quantum experiments have had issues with electrical wire in the building. Could be a pump next door, could be something coming down the lines. But this is often enough to upset the vision of the system. So what we did was sort of think a bit about what would help. And what we ended up with is the use, for instance, of a separate transformer. So we have a direct line from our lab actual transformer that we don't share. You don't want any other person using that line. We have neutral screen cable. What that means is we use power that's coming out of coaxial cable. And the beauty of coaxial cable is it doesn't generate any magnetic fields and it doesn't respond to any magnetic fields. Okay? Currents are balanced, there's no net issue. So that's quite important. And also we bring all our cables, all our power cables coming in from the top. So there's nothing around the walls. We can keep them kind of away from the experiments. And this seems to work well. You still get distortion in the waveform because you've got your own instruments, but nevertheless you can get a good result. I just mentioned a particular example where cryogenic current comparator, you probably need to understand this too much, but basically you've got coils with thousands of turns coupled to a squid. The squids are very sensitive dulcity flux, and so you really ask for trouble because you've got all these turns picking up noise and so on. So they're notoriously difficult to operate, and normally they take weeks of tuning to get rid of the noise. We bought a new system through the PTP in Germany, and it pretty much worked from day one. And people were very amazed by that. And you don't expect this very sensitive system to work, and yet it did. And I attribute that to the way we did the power. So again, if you're developing the economy, you want to build a lab where you can do some good measurements, and think about your power distribution carefully. Because the most important facility you have is what the group you're working with. If that's not if it's causing you problems, you never progress well. So think about your group as well. Okay, and finally, I just want to mention international collaboration. So as an NMI, National Measurement Institute, we're part of a worldwide network, and particularly an Asia Pacific network known as APEC. And you can see here the sort of mandate of what APEC is about. Cooperating in terms of sharing expertise and exchanging technical services. combined with several regional organisations, but it also has this connection with APEC, which I haven't really appreciated too much. I don't quite know how that's operating, but nevertheless, both organisations have the sense that we are, we are probably better together, which is, okay, the bigger nations have enough progress, but we want the small nations to come along and develop as well. And also APP covers this enormous area of the world, and very close overlap with APEC, characterised by an extreme diversity of scale. We're from China, India, the biggest nations in the world, to some of the Pacific Islands, some of the smallest. We're all part of the same group. 46 full economies, and there's also social economies as well. How APP works, there's technical committees, obviously covering all of the metrology, relief, mass, time, and so on. But nevertheless, the interactive committee deals a lot with quantum systems, and so we cooperate each other in terms of running these systems. In terms of activities, there's a general assembly, there's annual meetings, workshops, there's comparisons where we make sure we get the same results for the same artifact. And this is really important if you're trying to make some claim about the performance of something. No one's going to believe you until you can prove it by someone else. So you need to work together to sort of validate each other's progress. So there's a peer review to support accreditation. Joint projects, we don't really have a source of funding in this body. The European equivalent, Euromet, has a very large amount of funding. This is the way they work. But we just generally do individually funded projects. But we do attachment training. I think we already talked about that. It's quite important for growing labs to be able to send their staff to learn quickly. They want to sort of reinvent the wheel. So, sharing staff around is a very quick way to develop expertise and skills. And they can work in both directions. Sharing shared devices, shared artifacts. And finally, we support particularly developing economies, which seems to be very relevant to APEC. So, I guess I'm just putting forward this model of how Asia Pacific economies can work together. It's a little bit awkward because it's really limited to the national research institutes. And there seems to be some overlap. And I think in terms of the mechanism of how we operate in the future, there may be some way we can bring the two together. So that's my summary. All right, thank you.
Question?
Questions. Also, in many countries, NMI has the role of the national hub for quantum technology. It's the same as in New Zealand.
Yes, so we have the quantum standards, and we also get involved in a number of things. There's a random quantum number generator, single photons, even a little bit of encryption. Because we have the understanding of quantum systems is a little bit broader, but the core is the Jefferson system.
Second question is the building construction. KRISS has a similar building construction years ago, but the energy consumption to maintain the experimental environment requires a lot of the energy for fluid cost. Rather than the condition. So, how about
Well, we are fortunate to have a fairly mild climate generally. It doesn't get too hot, and it actually doesn't get that cold either. So, in principle, we could operate quite an efficient system by just simply warming the air a little bit. But to do it in summer, you still need some cooling. But it's a little easier for us than some of the hot countries, for sure. But that's what we do. Keep everything, keep the lights on, keep everything stable. I guess I don't pay the panels.
Any other question? Okay.
Okay, so next session is the final session where we'll have three presentation and also some discussion. So those of you whom I call will wait here for so discount. Michael Brennan, is it? Michael Brennan, are you here? So you're supposed to be here, right? I will appreciate. And Jared Cole, Gerald Cole, yeah, you'll be here. Okay. And Alexander yeah, be here. And I will invite you. Gavin, you spoke already. Ujubi also, okay, good. Sunguli, okay, good. And Yongsu Kim, okay. And Jinny Kim, I would also invite Jinny Kim. So we'll meet you here again at 24. And in the next session, the last session for collaboration, we'll have a presentation and also discussion session. Thank you very much. And then we will have we'll leave for dinner. So we will attend here and then we'll move together for dinner. Okay?
됐어. 마지막에 내일 가잖아요. 아시죠? 거기서 기다리실 거죠? 같이 가실 건가요? 기다리실 거죠? 삼계탕으로 준비했다고 그래. 저희서 할 거야? 저희서? 한정씨 집에 갈 거야? 같이 갈 거야? 갈 거야? 카운터 하자. 하나, 둘, 셋. 소희 박사, 저희서 같이 가실 거야? 어디요? 저녁 식사.
저희
총회가 있었어요. 알죠? 제가 거의 여기도 시간 진짜요. 그것 때문에
저희 또 총회하고 평년에
이게 이거
제 여기는 끝나고
오시게 돼요.
from CSR.